What's up mga kache? It's Kuya Dale here. So I'm back with another chemistry lesson, and maybe this will take or not take quite a long time than my previous lesson on the chemistry in the atmosphere. So if you haven't seen it yet, so I will post a link in the upper right hand corner of the screen, and be sure to watch it and ace your exams. And now let's begin. So Okay, so our lesson this time is about the chemistry of the hydrosphere. So this is still under the chemistry for engineers course taken up during the first year of the chemical engineering program. So this will be the contents of the presentation. So first we'll be discovering the unique properties of water, and then we'll see how water exists in nature, and then its chemical and biological contamination, so what contaminates it chemically and biologically, and then the favorites of chemical engineer, which is the industrial water use, and then the groundwater contamination. So how is our groundwater contaminated, and then making water fit to drink. So I'll be discussing also the Philippine national standards for drinking water this time, and then my favorite is the uh, wastewater treatment. So it's the chemical engineering thing. Okay. So next, let's discover the unique properties of water. So its solid form is less dense than the liquid. Why? It's because um, there is more mass in the liquid than in a solid in the given volume. So if you can, as you can see here, in a given volume, there are a lot more water molecules in the liquid form than in the solid form, right? As you can see, there's a lot more here than in the solid form here. So it um, at 4 degrees Celsius, so if we are being really technical here, so at 4 degrees Celsius, the density of the water, the liquid water, is 1,000 kilograms per cubic meter. And then, if we look at the ice, which is solid form of water, at 0 degrees Celsius, which is the freezing point of water, the density of the ice is 920 kilograms per cubic meter. So as you can see, it's really lighter than the liquid water. That's because there are only a few water molecules in a given volume. So maybe in a cubic meter, this much water molecules have been it's that is contributing to its weight, right? So uh, and also, as you can see here, water expands as it freezes. Why? Because it takes on a more ordered arrangement. Not unlike the liquid one, it takes on a more um, arranged configuration. It it forms four hydrogen bonds per molecule. So the solid ice contains large hexagonal holes. So large hexagonal holes, just like you see here. And then this three-dimensional structure extends out for billions and billions of molecules. So when ice melts, these holes collapse. So this will be no more, and then it will become liquid like here. So this explains why ice is less dense than water. All right. So I've explained that. Maybe I over communicated it to you that it's because there are only less um, molecules in a given volume in ice than in its liquid form. So as you can see, if water is slowly frozen, then you can form a snowflake. So just like a beautiful snowflake here. This is good for aesthetic purposes, but not for freezing food. If water is being frozen quickly, so you cannot form these beautiful snowflakes. what the industries do is flash freezing. So they use flash frozen foods. They freeze. So as the name suggests, they freeze it in a little as little time as possible to preserve the food and so as not to damage the cellular structure of the food by these snowflakes. So imagine if you are freezing your food slowly, then these snowflakes will form, and then if snowflakes will form, your food will be damaged, right? So it's not as palatable anymore, and maybe um, the taste that you are looking for is being damaged by these snowflakes because it's freezing. It has been frozen um, quickly. So imagine if your tocino will be frozen slowly. The taste the taste will not be the same anymore, right? So that's how it is applied in the industry. So second, uh, it is denser than most other common liquids. So water, so as I've said, it has at 4 degrees Celsius, it has the density of um, 1,000 kilograms per cubic meter. And maybe for oil, you can find these commonly around 800 kilograms per cubic meter. And then for um, for alcohol, maybe 890 kilograms per cubic meter. So that's the typical densities of these liquids. So water is a lot denser than most other common liquids. Why? It's because of its intermolecular forces. So intermolecular forces of attraction. So I've explained it to you in the last lesson that we have three intermolecular forces of attraction. So that is the hydrogen. First is the van der Waals forces, and then the dipole-dipole moment, and then the hydrogen bonding. So as you can see, water has the strongest IMFA. Water is the strongest IMFA because it has hydrogen bonding, right? Oil, on the other hand, has van der Waals and dipole-dipole moment only. Dipole-dipole moment only. So it's really as strong as the water. So as a consequence, it does not really clump together. So as I will show you a molecular structure of an oil. So as you can see, it is really a big molecule compared to water. You have a hard time stacking these together to have a stronger IMFA because of its structure. So if you are being in you are in organic chemistry level already, so you can see that what makes it a liquid is because of the unsaturated bonds here. So the double bonds. So that's what makes it a liquid. And liquids in oil, so it has a lesser um, IMFA because it can't stack together, right? It can't stack together, so it meaning it has a lower boiling point. So that has really it has many uh, implications on why that happens. But one explanation is that you have a lower or I mean weaker IMFA, right? And then if you compare it to alcohol, which is slightly higher than oil, it's because you can easily stack together. You can easily stack these together. And also, if you can notice here, we have the OH here, right? Also have OH, suggesting that we also have hydrogen bonding, right? So if you have hydrogen bonding, so maybe this can compare to water, but it also has our hydrocarbons which make it non-polar. So as you know, water is a polar molecule, and then also alcohol is has a polar part and a non-polar part, and that contributes to its IMFA. So it has a dipole-dipole moment, and also it has the hydrogen bonding. Right? So you can easily stack these together. So it that's how it will be explained using the density. It's because of their IMFA. And lastly, the 3 to 4, the last two unique properties of water is that it has a high specific heat and a high heat of vaporization. So you can see the the heat capacity. It's the capability for a molecule to absorb heat energy. So water's high heat capacity is a property caused by hydrogen bonding. So hydrogen bonding happen. Hydrogen bonding. Um, Hydrogen bonding among water molecules. So when heat is absorbed, the hydrogen bonds are broken and water molecules can move freely. Right? So when the temperature of water decreases, the hydrogen bonds are formed and release a considerable amount of energy. And then water has the highest specific heat capacity of any liquid. So specific heat is defined as the amount of heat 1 gram of a substance must absorb or lose to change its temperature by 1 degree Celsius. So for water, so as you can maybe know, so as you already know, so the CP or the heat capacity of water is 4.184 joules per gram per degree Celsius. So this is how much heat you have to apply to water, to 1 gram of water to raise its temperature by 1 degree Celsius. So that's what it means. You have to input this amount of energy, 4.184 or 1 calories per gram per degree Celsius. That's how um, that's the amount of energy you have to input in water. So you have to yeah. So you have to input in the water, and as a result, it takes water a long time to heat and a long time to cool. So in fact, the specific heat capacity of water is about 5 times more than that of sun. So this explains why land cools faster than the sea. And also, this property of water is very important. It's because if we do not have the water, so as you can read in your book, so I was fascinated by this fact that because of the water in the earth, uh, it serves as a large heat sink and a large heat reservoir. Why is that? Because when the sun shines, so when the sun shines in the, so if I can uh, erase this so that I have uh, space to write. So when the sun shines in on the earth, so there are a lot of energy that will be absorbed by the heat that will be absorbed by the earth. But what if the sun will not shine in the, or the earth has already rotated on the other side, so it's maybe it's nighttime, right? So it's nighttime, so if the sun will not shine, so the temperature will lower, right? So if it lowers, then that is a, if it lowers below negative, below zero, so it becomes negative, and it cannot the earth cannot supply and that cannot support life anymore. So as you can see, this let's put it here is the moon. So here's the moon. So imagine at noontime in the moon, the temperature can rise as high as 100 degrees Celsius. So that's very hot. It's equivalent to boiling water, temperature of boiling water. And at nighttime, when the sun is not shining in that side of the moon anymore, it can go below as 100, a negative 100 uh, 73 degrees Celsius. So that's very cold. So you can see the water in our Earth keeps the temperature of the Earth rising up to 100 degrees Celsius because of its high heat capacity, which is 4.184 184 joules per uh, degree Celsius, and it prevents also us to go below. It prevents also the Earth's temperature to go below 100 negative 100 degrees Celsius. So that's really a fascinating fact. So I just knew about it. So I'm sharing it to you so that you'd be informed as well. All right. So it's so much about this. So let's move on. So let's move on to water in nature. So water in nature, as you can see, I have shown you here a um, water cycle. So first, the evaporation. So first, the water from the seas or any bodies of water uh, goes above. So it goes above the troposphere. So it lands in that part of the atmosphere, and then also it absorbs the sun absorbs also, or it evaporates also water from the plants by transpiration, and then it as it goes to the top, uh, it condenses, forming the clouds. So when water is saturated in the clouds, so water is saturated in the clouds, so precipitation happens if the clouds cannot hold the water anymore. So precipitation happens, and the rainwater becomes part of the ice caps. So if this mountain is really high enough, so maybe as ice in it, so it has ice caps, runs off in streams and rivers and fills lakes underground. So here, the lakes and underground pools of water in rocks and sand called aquifers. So this is an aquifer. So under the rocks and the sand below the land, below the mountain, you can find pools of water that's called an aquifer. And as you can see, as we discussed in our previous lecture in chemistry in the atmosphere, rainwater is not pure water actually. So it carries down dust particles. So if there are many, for example, if this takes place in a largely urbanized area, so you can see uh, dust being emitted or being thrown off the atmosphere. So it has the rainwater carries down dust particles and it dissolves some oxygen, nitrogen, then actually carbon dioxide as it falls to the atmosphere. So the carbon dioxide makes natural rainwater acidic. So uh, this is actually the water. Uh, Carbon dioxide makes the natural rainwater acidic because it reacts with water to form carbonic acid. So I'll show you here the equation. So H2O plus CO2 forms carbonic acid, H2CO3. And this is also the acid that is on our in our soft drinks. So if you open a bottle of a soft drink, as you can see, it fizzes, right? Fizzes, so bubbles come out. So this is actually the carbonic acid that is being decomposed into water and CO2, because CO2 is being dissolved in the water in our soft drink as it if you really If you open that bottle of soft drink, it goes back to being CO2 and H2O, especially if it is already warm, right? So I have mentioned also in the previous lesson that when there is lightning, the nitrogen in the atmosphere will react with oxygen, forming nitrogen dioxide. So forming nitrogen dioxide, and there is water in the atmosphere. So meaning uh, it produces also nitric acid, which is part of acid rain, right? Nitric acid. And as also, we will talk about groundwater. So as water moves along or beneath the surface of the earth, so this is not stationary, it moves, all right. So it dissolves minerals from rocks and soil. So this is now called hard water. You can see this in your faucets actually. And if you have noticed, especially if water supply in your area is not treated whatsoever, the faucets in your home will have minerals that will stick on them. So you'll have a white thing that, yeah, it's really hard to remove, and it sticks in your faucets. And it usually they are white, as if dissolved limestone came out of your faucet and stuck up there. Mabara. So, bara in yung faucet. Second is when you are washing your clothes. If you notice that instead of detergent cleaning your clothes, it will react with the calcium and magnesium in hard water um, to form scum. So if you can see those little white powdery material uh, that will be formed if you are washing your clothes, right? So it actually cannot wash your clothes anymore because it has reacted with the soap or the detergent. All right. So also, uh, as rainwater, as I have mentioned earlier, that it is slightly acidic, right? It also dissolves matter from decaying plants and animals. So this organic matter, so I have put here organic matter, so are actually polluting our aquifers. All right. Now, they may come in the forms of traces of lubricants and fuels, some fertilizers, pesticides, and bacteria, microorganisms, and animal wastes are all potential contaminants of natural waters. So, check applications. So, I really love to share check applications to you. It's softening technology. So this is in a plant setup. So as you can see, 'di ba? I've told you that there are water in below that is called our groundwater or the aquifers. So it is being drilled and then it is being used in the plants. So using deep well. So they dig below in the ground. So wala siyang atabay if in the local language. So it's atabay, but it is closed. You can't see the opening you can't see its opening in the if you go in the plant. All right. So they filter that and then they dose it with chlorine. Why? For disinfection, right? And then they store it in a large, very large, very large. You can fathom its size. It's a reinforced tank storage. It's really large. So that's the water supply of the whole plant. So comes from the uh, deep well that is drilled and then it's stored in the reinforced tanks or RC, reinforced concrete tank storage. And then it goes in two ways. All right. So some of it goes in the demineralization plant. So demineralization, as the name suggests, it will remove the minerals such as the calcium 2 plus, the magnesium 2 plus, the uh, Na plus, all metals in the water that makes it uh, a conductor of electricity. So if you remove these ions, the water now becomes uh, an insulator, a pure water, because you have removed these electrolytes there. So it will not conduct electricity anymore. And then it will be stored in the demineralized water, or DW, demineralized water tanks, and then it is being used as water in our boilers. All right, so the water that is used in our boilers is demineralized water. Right. And then we have also the second part, we have the water softeners. So water softeners, they just remove these two. So that not really remove the uh, all minerals in water, but they remove the hardness of water. So calcium and magnesium, and then they usually use um, ion exchange technology for this. So this soft water, I will explain to you how they do this in the plant, and then this soft water will be stored in the soft water tank, and then it will be supplied in the uh, production lines in the tank, in the plant I'm sorry, will be supplied in the production lines of the plant. So how is the soft water or the ion exchange technology being done? So this is how it's being done in the plant. So you have the hard water here, hard water that's full of hardness, the magnesium and the calcium. They exist as calcium carbonate and magnesium carbonate. So calcium carbonate and magnesium carbonate. So they exist in nature as that. So I just wrote this and Ca2 plus and Mg2 plus, right? So to show that they are ions already. And then the hard water goes into here, and then what happens here, you have resins here, you have resin, which have the sodium ions embedded in them. So, as you can see, if this is a resin, this is a resin, the 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 job now of the water softener is to replace the ions in our the ions in our water with Na, or with sodium. So calcium goes through here, and then sodium leaves. So now it becomes uh, Ca here, and then the sodium ions will go with your water, making it soft water, and then it will not clog your pipings in your plant. So it will not clog anymore. As I discussed in the chemistry in the atmosphere lesson, diba? This will deplete in time. All right. So over time, it will be depleted. So how do you replenish the Na here, the sodium here? So you have to regenerate your resin through regeneration. This is the regeneration part of your ion exchange cycle. So the plant uses brine solution or asin, ibutang sa tubig, and then that will replace the calcium and magnesium that were embedded in our resin. It will be replaced with um, sodium ions. All right, so that's how they replenish the sodium ions in our resin, and then it will be ready for use for another cycle of ion exchange or water softening technology. Okay, so next, so we have the chemical and biological contamination. So first is the waterborne diseases. So as you can see, there are many bacteria, there are many viruses, but mostly bacteria and actually fungus in our water bodies. So you can see we have diseases caused by drinking polluted water. We have cholera, giardia, hepatitis A, diarrhea, typhoid, right? Maybe if you factor in amoeba here, so it will make your stomach hurt, and uh, you know what happens. And then one of the contributors of that is having no proper um, septic tank, right? If you just dig a hole in your community, and then you it has no proper uh, it has no um, walls, so it has no it will leak. Actually, it will leak, and then it will go to the water supply of your neighborhood, which is the deep well. And you know, some use this for drinking, and then they will get the disease. So that's one of the causes of uh, or one of the contaminants of our water. Second is our acid rain. So I have discussed this already. I will not go through in depth. Just know that that it is being produced by the exhaust of our industrial plants and also of our vehicles. So we have SOx and NOx here. They will form nitric acid and then sulfuric acid, and then it will produce acid rain. All right. Then sewage and dying lakes. So you have performed this experiment in your chem lab, the measure of the determination of your DO or dissolved oxygen. So what happens here as your factory um, disposes its waste uh, in the bodies of water. So it will have many contaminants there. So one of the measure of the contamination level is our BOD, or the biochemical oxygen demand. So biochemical oxygen demand. So if it is high, so the higher the BOD, meaning the higher the BOD, the more polluted your water is, because the it is the demand or the oxygen required to decompose the organic matter that is being thrown in your bodies of water. So that's how the um, BOD works. So it tells you how polluted your water is. So it is really high, really high. So it will form maybe an algal bloom there, and also it's one of the results of dumping too much organic matter. For example, we have your for para makarelate mo, that you can relate. uh, for example, it's planting season, and uh, after that maybe you put in your fertilizer, and then when the rain comes, the fertilizer in your plant, in your field will go down to your water, and then imagine that has many nutrients. So that many nutrients will cause an algal bloom here. So that is what is called eutrophication. So that is what called that's what is called eutrophication. So you will cause an algal bloom here because of many nutrients that is being dumped on the bodies of water. So imagine if there's being an there will be an algal bloom there that's really happened in Boracay last year. So what happened though? So they closed it. They cleaned it because the water is not as beautiful as it is anymore, and it contributed to fish kill, right? Because as BOD goes up, dissolved oxygen goes down, all right? Because it uses up the dissolved oxygen in your bodies of water. So that's how important it is. So um, yeah, so that's how important it is to remove those nutrients before dumping it in the uh, bodies of water. So I will explain it further to you in the later part how this is being done. All right. So industrial water use. So in the table in your book has many contents, or um, shall I say, contributors of the industrial water use. So the largest in there, the largest consumer of water there is the making of one laptop. So I can't relate on how laptops are being made, but I can relate how paper is being made because I have gone to a paper making company during our plant tour. So as you can see, guys, uh, it paper making consumes 20 cubic meters per metric ton. So actually, paper is being produced by rolls. Paper is being um, produced by rolls, and then they weigh it. So if it is uh, per 1,000 kilograms per 1,000 kilograms, it consumes 20 cubic meters. So that is equivalent to, if you can fathom it, if you can picture it, just imagine 3,334 pieces of 6 liters bottled water per metric ton of paper. So we have this imagination, or uh, how we picture things, or how we measure its size by uh, comparing it to things we know. So, for example, if 20 cubic meters, so amo na siyang gina scale by hala pila na ka 6 liters nga absolute nga drinking water. Kada kang galon dito sa absolute nga na. Then mo hala daghan na gid kay no nga na ang pagkuan sa una. But maybe you can use your own. You can use your own. So, paper making really has a large water consumption because um, I have been to a paper making plant, but they don't use virgin pulp wood, right? So they use recycled recycled water. So recycled carton, recycled paper. So imagine in all those process, you have your washer, you have to screen that. This uses a lot of water actually. This uses a lot of water. You have to clean it, you have to thicken it, and then you have to bleach it because um, as you can see, cartons are uh, not clean when it is being brought into the plant. So you have to bleach them. Uh, yeah, and then you have to form them, and then this is what is called a fourdrinier. So maybe I can put a link of a how paper is being made in the plant, so that you can imagine how water is really being used in a paper making company. It's really huge consumer of water. It's a large water hub. It's a water hub. Yeah, and then it is being washed here also. It's being washed, and then it's being dried, and then you can see that if you I will put a link in the description or the upper right hand corner of the screen, so that you can see how paper is being made and how it is large water hub. All right. Groundwater contamination. So as I explained earlier, so nitrates. So nitrates, diba? If nitrates, this is the cause of eutrophication. So this is one of the um, components of your fertilizer, your nitrates. So if it, so fertilizers, so it also affects our aquifer, right? So large pools of water underground, and then we have our septic tank. We have leaking underground storage tanks. So you know, if your septic tank is not built away from the water table, it might contaminate your aquifer, and then it is the source of water in your community, and it will be will be contaminated, and your house happened to be nearby it. Imagine what headache that would be to the residents. And then volatile organic chemicals made, usually these are um, things that is being sprayed, or maybe um, one example of this is the paint, spray paint. Actually, you have seen this. You have seen um, a lot of examples of this in your book, right? So you can read this in your book. There are lot of contributors to groundwater contamination, and I will not be dwelling on that. So making water fit to drink. So in your book, it only stated there the United States. So it's the United States standards of drinking water. But in here, I am presenting to you the Philippine National Standard for Drinking Water. So PNSW, Philippine National Standards for Drinking Water. So as you can see, uh, what's the standards for bacteriological quality? So for your water to be drinkable, it should have no, also zero fecal coliform bacteria in your water. So number per 100 ml of the sample of your water must have no E. coli, or ana, must have no E. coli. And then the pesticides, or the other insecticides that is being monitored in the water level. So you have the heavy metals here: antimony, arsenic, barium, boron. These are heavy metals, right? And then selenium. And then next is our pesticides. So pesticides, these are being regulated, and then their concentration levels are being monitored in the drinking water levels. So the maximum level must be 0.03 in the aldrin and dieldrin. So these are insecticides, by the way, especially DDT. Your, this is famous in the 70s. Dichlorodiphenyl trichloroethane. So that's DDT and Endrin. So you can see this. The Philippines put this into law, these standards, so that the safety of the citizens will be ensured. All right. So that's what the Philippines version of the U.S. United States version of what you have seen in your book. So it is the PNSW. So now we have our water treatment plants. So I have seen one water treatment plant in here in our place in Cagayan de Oro, and actually it's not in Cagayan de Oro, but it's in Bidnon. Is the Rio Verde water. So they provide the water actually to COWD, okay, again the Oro Water District. So if you are a customer of COWD, it's likely that your water came from Rio Verde. So what happens in Rio Verde, or what happens in a water treatment plant? Okay, so I have seen it, and their water comes from Bubunawan River. So what they do there is that the water is not really clean. All right, so it is being used for farm purposes. So it's being used for irrigation. So what they use there, so what first things that they will do is that they will put coagulants in the water, and also flocculants. So the functions of these chemicals, for example, this alum and chlorine dioxide. So let's work on the alum first, which is our flocculant or coagulant. So there are things, or there are materials, there are particles in your water that will not settle. So these are called colloids. These are called colloids because they are not big enough to sink. So they're just there in the and they are not fine enough for them to be considered a solution in water. So water is actually has many particles there, and then they have colloids there. So what happens is that this alum here will act as a coagulant. So what it does it attracts the particles together, and then they will clump. So this is what called the flocculation. It will clump, and then it will be removed by sedimentation. So because it is heavy enough to sink. So as you can see here, there are fine particles here, and then if it is being reacted with alum, they will clump together, and then they will become large enough for them to sink, for them to be removed also by sedimentation. So they will settle in the bottom, all right, and then they will be collected in the drying basins, and then the water now that is removed of those particles, those large particles, they will go to filtration. So usually this is a sand filter. The sand filter goes through all stages, and then maybe gravel, and then the bottom part is the fine sand there. So if the water now is being called a clear, that it's relatively clear, guys. If you have the opportunity to go to Rio Verde, you will be amazed. And then they will put these kinds of materials for it to be disinfected, right? Disinfected to clean the water further, and then it will be stored in the storage box. And then actually the last part of the water treatment in that plant is called, you will see a clear water there. So they have this is called a beauty box. So because you can really see that it is really clear, the water is really clear, and then it has at the end of the process, you have a flowing water there in the faucet, and you can drink freely there. And because you've seen the process, you can assure that it's really clean. And I also drank from there, of course, and I can really assure you that it's good, right? And then it will be uh, stored, and then it will be distributed here in the lower parts of the city. All right. So that's how water is being treated. And also, if you didn't get what I have been uh, discussing here, I will put a link in the upper right hand corner of the screen for you to see how water is being treated. All right. And then lastly, my favorite, the wastewater treatment plant. So, because I have been, this is also my job in the last OJT, in my last OJT. So I was assigned in the wastewater treatment plant of uh, the plant that I was assigned to. So we have here, as you can see, if you can read this in your book, we have the primary treatment and then your secondary treatment. So primary treatment, as you can maybe if you have hard time differentiating between primary and secondary treatment, so I can uh, I can help you. So maybe you can memorize it as such. So primary treatment takes care of the physical characteristics of your water. And then the physical qualities of water, and then your secondary treatment takes care of the chemical. part of your water, and then your tertiary, so you have tertiary, takes care of the biological takes care of the biological part of your wastewater. So what happens in a wastewater treatment plant? So you have a raw sewage. So for example, this is a water wastewater in your plant, and then it will go to a screen. So has it goes to a screen to filter out, maybe they have a bottles there, the bottle caps there that will damage your pumps in your wastewater plant. So you don't want that to happen, so you have to remove that as early as in the early stage in your wastewater treatment plant process. So then you have your comminutor. So if there are things, if there are particles there that maybe if you, let's just say, hard soil that is being that went through your screen, it passed through your screen and then will pass through your comminutor. So the function of the comminutor is to reduce the size of those particles. If they are being clumped together, they will be broken down by your comminutor. And then you will have your primary clarifier. So the primary clarifier um, um, basically works as a sedimentation tank. So sedimentation tank, it's really a large circular um, sedimentation tank in the plant, and it's really muddy. In the first time that you it will go through the primary clarifier, so it really is muddy. The waters are murky, and then the goal there is to let the heavier parts of um, the muddy part of your wastewater to settle down so that it will be collected as sludge here. So it will go to sludge treatment and disposal. So I will talk about that later. So I just hang in there. So the water now, being relatively clear from the primary clarifier, goes through the aeration tank. So this is called the activated sludge process. Activated sludge process. So what happens here is that you have bacteria here. You have your aerobic bacteria here. You have aerobic bacteria here that will consume your organic matter in your um, that will consume your organic matter in your wastewater. So notice that the physical parts of the physical contaminants in your wastewater was being removed first here in your primary clarifier, right? So it takes care of the soil, the mud that will be removed from your wastewater before it is being treated in your aeration tank or the secondary treatment, which takes care of your chemical parameters. All right. So you have bacteria here, your aerobic bacteria that will consume your organic matter here, and then we have many parameters that will be checked here: your pH, your temperature, your DO, your BOD, and most importantly, your COD. And it's not cash on delivery, huh? But it's oxygen demand, chemical oxygen demand (COD). So it's biochemical oxygen demand, and then it's your chemical oxygen demand, right? Chemical oxygen demand. And then if the certain time has passed, and then it is being set in the plant that at this time all or the level of your DO and your BOD is enough is enough. So it will pass the DENR standards, and then it will go through the secondary clarifier, because the all not all of the mud, or no, all of the soil it's being removed here. So you have your products of your uh, consumed organic matter here, right? So all of them also, those products also uh, will settle. So it will be removed further from your removed further from your wastewater, and then it is relatively clear now. So you now have to add a disinfectant. So you have, and this will go through the on any body of water. Yeah, maybe it's a sea or a river. So it may be where what they do is that before they discharge it to any body of water, they let it pass through a fish pond. So you have fishes there. So you have a koi bakaha, koi, usually koi in that fish pond. And if those fishes will die, meaning your the DO, the dissolved oxygen levels of um, your wastewater is bad. So it's really low. So it cannot support life, right? So it cannot support life. So you will have to make adjustments here to for the DO to be higher, so that it will support life in the water body of water that you are throwing the wastewater to. Yeah. So that's how it is. So actually, I also will post a um, video here, siguro in the upper right hand corner of the screen for you to watch, so that you will see what I am talking about. Right? And then nako, we have actually there was one student that asked me where the uh, sulfuric acid and the nitric acid from this gas scrubber, right? You asked me where it will go. So it will be being treated here, actually, in the wastewater treatment plant. So we have this pH adjustment, pH adjustment in the pH adjustment in the plant. So it's acidic, right? So it's acidic, pH adjustment. So you have to add a base, so that you have the pH will go up, and then it will not kill your microorganisms here that is consuming your organic matter. All right. So that's it. That's in what wastewater treatment plant. So in your book also we have the tertiary treatments. You have the charcoal filtration, which takes care of the impurities of your wastewater, so that it can be there are it can be drunk, or it can be drunk again. So if you see, it has many applications. Actually, kung gusto nimo, if you want to deodorize your ref, you can put activated charcoal there, di ba? Pwede butangan ganyan uling. For some, they put charcoal in there to uh, get rid of the bad smell in your refrigerators. And also, we have reverse osmosis. You can learn this in your practical technology. But what it does is it forces this impure water in a semi-permeable membrane, and then the particles there that is being left out because it cannot go through the holes in our semi-permeable membrane, it will be left out, and then what comes out is a uh, relatively cleaner, purer water, because it filtered out the bacteria or virus here, here in the uh, here in our water. So it's form of filtration also and form of disinfection, right? And then lastly, we have our phytoremediation, which uses plants, which uses plants that will absorb or take up the nutrients that is being uh, nutrients that was left in your um, wastewater, maybe in the mouth of the river. Yeah. So this consumes the nutrients that is being thrown from your plant. Okay. So that's how phytoremediation works. Also, you can read this more in your book. All right. So actually, that ends our lesson in the chemistry of the hydrosphere. And sorry, it took so long because I really have a lot to say. So if you have any questions, you know where to find me. And this is the book that I used, Hill and Kolb Chemistry for Changing Times. So I also post my contact details in the um, description box below. And don't forget to, if you haven't subscribed yet, so please subscribe, like, and share. So your support means really means a lot to us, and actually it drives me more and it inspires me more to create more videos like this in the future. All right, so that's it. Bye bye. Thank you for watching.